in its own grade. So then she marked it informal. But then when I spoke to Emer about it, I told her, no, I didn't even tell her anything. I just told her, can I know why this is informal? She said it's not. And then she said maybe she wrote it, she penalized you for it because a mentality cannot take its own grade.
That's what I was thinking when you said it.
I retaliated by saying that it's personification, which is another linguistic technique.
True, but these are advanced terms. Needs to be done perfectly or it just is a mess up. So I wouldn't want to comment on it without actually seeing what you wrote. But from reading your physics essay, I kind of get it. Because you use blasphemous, which is nice, but I don't feel like you execute it perfectly. And when you're using such advanced English, it needs to be perfect or not at all.
Yeah, but
so I'm sorry.
It was taken for recheck though, because after I stated that it was personification and there were linguistic techniques, she started doubting herself and she took it for rechecking.
Okay, that's fair enough. But let's just say if I was a betting man, which I sometimes am, I wouldn't be putting large money on you right now. Maybe €2. I'd risk €2.
Better than nothing.
Yeah. Okay.
I promise you, I'll get like 4 back.
Fair enough. Right, what lesson is this? Maths or physics? Physics. Yes, we're starting the final lesson in the materials. Nice. Faisal, please get off your phone. You said you tried to be good. Materials, Young's modulus.
was I even close to an 8-type? I want to know my percentage.
Might have been like a 78 or something.
Why did you do this to me?
Somebody who got a C.
It was very close to an 8.
I think it was you. I think I left you hanging on a 59.
Oh.
I know.
Why?
Harsh, huh? Oh, I suck, I know. And I like it. Okay. Look, to be honest, the assignment was stupid and the essay was stupid. I think it's a stupid thing to have to do, but I have to do it.
This is the first year,
yeah. Yeah. And sure, it might turn out that I was marking too harshly and they'll bring everyone up. I just have no idea.
Sure.
Can they bring someone down?
Of course.
Yes, and that's only happened once with one person. It's more likely to go up than to go down. Most likely is not to change. Yeah. Okay, Young's modulus, please. But anyways, the people who got a C, really they got the C because the introduction and conclusion were terrible and the main body was excellent. But unfortunately, the main body was only 40%. So for example,
So you only get 40%?
No, for example, like for you, I would have given you like an A for the main body. Or for whoever else got a C. But then for the introduction and conclusion, I wouldn't have given an A. But unfortunately, the introduction and conclusion are worth 40% and the main body is worth 40%. So because of that, it comes down to a C then.
Did everyone get the referencing right?
Mm-hmm.
Oh yeah, I was happy enough with the referencing. Yeah. And some people had nice graphics in it too. Your graphic, yours was the man on the earth, was it? You travel 8,000 meters and you fall 5 meters. Yeah, I thought that was cute graphic. It looked like you made it yourself. Did you? No, it looked like it. It had a nice home feel about it. Yes. Okay. And then Yahya, where is he?
He had to go by diploma.
I have to say I was very happy with people's explanations of the GPS systems, the maths involved, that you need 4 satellites and all this stuff. I thought everybody did a great job of explaining GPS. Really, good job. The only drawback was the introduction and conclusion, especially the conclusion. But I know this is the type of stuff students have trouble with, you know. But anyways, I hope you're not disappointed, because I was actually very happy with what I was reading, but I have to mark according to the scheme I'm given, and the scheme I'm given only gives 40% to the main body, which I think it should be worth more because it's the main body. but it's only 40%, and I'm sorry about that, even though what you wrote was really good.
Can we get them back? Can we read them? Because like I wanna use them like to have me for my chemistry essay.
Who's your chemistry teacher?
The-
Right. She will not mark the same way I will.
Okay.
I don't know. I can give you some feedback. Yes, I can. Okay. Young's modulus. So, does anyone know this word, deformation? What's it mean?
Change shape.
Yes, but it's
I'm not sure.
I think. No?
Not necessarily. Not necessarily. Simply put, is a change in the shape. And for us, that would be the length, because that's what we're looking at in this chapter. Of a material by means of what? By looking at it? By what?
A force acting.
Yeah, a deforming force, a stressing force. This is the definition of deformation. Got it? Got it? I saw on the news today that a teenager student in South Carolina, America, died because he drank too many energy drinks.
There was also this man who drank a lot of Red Bulls and his heart inflated.
Yes? And exploded?
No, and he got wings.
Continuing. Yeah, no, because I had a student last year who drank a lot of Red Bull, and then one day in class he was sitting there, and all of a sudden he just went. I said, "Are you okay?" He says, "My chest feels strange." Like, which number Red Bull is that today? It's like number 3. Like, I'm looking at the clock, it's 11 o'clock in the morning. I'm like, not good. Okay, stress. Does anyone know this definition? Don't say to make Stephen angry. Not this. Does anyone know the stress on the material? No? I thought someone mentioned stress and strain a while ago. Do you know what stress is?
Sometimes people spoil the fun problem.
Indeed.
I'm trying to remember the formula for
Please start with us.
Go on.
He wants to be the one giving you the info, so I don't want to know.
Yeah, he doesn't want to steal my thunder. Okay. The stress on the material is the force acting on the material per unit area, cross-sectional area in fact. So, as a formula, it's force over area, correct. So, logically, what are the units here?
Newton per
Square. Thank you.
meter cubed.
Newton per meter squared, otherwise known as... Come on, wake up, children. Newton per meter squared is a... Thank you. Pascal. Continuing? Continuing? Yep. Lay! Look at me. Put the phone away.
I like your honor.
Open.
You know where you stand with Lee. You can trust him to give you an honest answer. Can you try to study? It's useless. Alright, fine. Okay, next is strain. And does anyone know this one? Strain. Anyone?
It's extension over something.
Yes.
Over length.
Yes. The strain on the material is the extension, x, over the natural length. The extension per natural length. So as a formula, it's x over L. And the units? It's unit free.
And then Young's modulus is strain over stress.
Got it exactly backwards. Okay, continue. So now that we have these terms, stress and strain, stress being a force per area and strain being an extension per length, we can introduce now the new term. Does everyone have this? Yes? Okay. New term, Young's modulus. Now, I use the letter Y, but I think the letter is actually an E. But I don't like using E because I use E for energy, so I use Y. Young's modulus of a material is the ratio of stress to strain. That is stress divided by strain. Continue. So what are the units for Y? What's the unit?
Pascal, yeah.
Pascal, correct. Clearly Pascal. Right. So, tensile strength now. But just before going on to that, I just want to have a look at a graph here for this. To see.
I think this is a little bit too much definitions for one lesson. They should have broken it down.
By they, you mean me.
Yeah.
And I'm sorry if 3 or 4 definitions is too much for you.
Not for me, no.
Oh, okay, you're thinking of your classmates. How kind of you. Classmates, are you okay? Yes? Everyone is okay? It's all good. Thanks for looking out for the class, Mr. Class Leader. Thank you. No, not class leader, class rep. Yes, yes. Stress over strain. Okay, so let's think of I don't know. You have some. You can either hang a weight on something or you can pull it. Which way would I like the graph? I think I would like to put strain here, and strain has no units, and then stress here. Although I could put it the other way. It depends on what I'm doing. So here I get stress equals Young's modulus by strain. So if this is on the y and this is on the x, then the modulus is like the slope. So you get a graph like this. The type of experiment could be something like this. You have a length here, and you pull it a distance here, delta x we'll say, and then you can, if I hook up my machine for measuring force, I can know the force here. So I can measure the strain, and I can measure the stress. So I get a straight graph like this. But then at some point what happens? It breaks. It would snap. It'd break. So I think that would mean, yeah, tell me what would happen here to the force if this breaks. What force would you get here if this breaks?
Force equals
0, because if the string breaks, then there's nothing pulling it anymore. So the graph would do what then?
It should like this or like this.
Which? Yes, I know. Which?
Like this, down.
Yeah. Because it has no stress, it's zero. In fact, really, it'll probably go something like this, because the stress is zero. But then also, the strain will be zero as well, because you're not stretching it anymore. So
Just flatten out and stop. The graph will just stop.
probably, yeah, it'll go like this. But in other words, it doesn't really make any sense here anymore. So the graph, it breaks here. There's a limit. When you have enough force, you break the rope. And this is kind of like the elastic limit, but it's a bit different because you're pulling it until it breaks, like physically breaks in two. And that's the next thing we're going to have a look at. But just before doing that, just let's have a look a little bit more at what Young's modulus is. It's stress, which is force over area, and strain, which is extension over length. So this would be length over area times force over extension. But remember, Hooke said force is K times extension. So this would be L over A times K. So you can see that Young's modulus is equal to length over area multiplied by K. So in other words, Young's modulus is proportional to K. Basically, Young's modulus is like a K. If K is big, it means it's very stiff and hard to move. Likewise, if Young's modulus is very big, it means the material is quite stiff and difficult to change its shape, difficult to deform. Okay, continue. Is that yay or nay?
Yeah.
Yay? Okay. Continue. So next we have tensile strength, and given what I was talking about, what do you think the tensile strength is?
You mean
Huh?
like formula or
No, in words.
the maximum point where a wire can hold itself without breaking?
You're right, you don't know. Anyone else? You're close though. Tensile strength is the force required to pull something such as a rope or a wire or a beam to a point where it breaks. So in other words, it's a breaking force. The minimum force required to break something. Obviously an important number in construction. You want to know what force would be required to break a structure.
I have a question. So does this mean that the force, tensile strength, is the force downwards or upwards?
Either. Whatever force is required to break something, basically. So,
Just look at it at directions. Because you can pull upwards and you can
Yeah.
pull downwards.
Yeah, but I mean like, if,
On the
let's say
ground?
it's suspended from the ceiling,
Yeah.
a string is
Yeah.
suspended from the ceiling, right, and we add like a weight to it.
yeah, it's the weight.
Tensile strength, is it the weight upwards?
In that case, the tensile strength is the weight you would need to hang on it to break the string. Yeah. Now, there is a context here. So, for example, if you're talking about like the tensile strength of a bridge, then it'd be the force required to put on the bridge for the bridge to collapse. So that's a downward case as well. But I don't know, if you had, I suppose most of the time you're looking at weights because you want to know when something will break. But I'm trying to think of a situation where you have the force maybe going up.
You have a wall or something. If you want
Yeah.
it to stand.
But the weight is acting down on the beam from the
Yeah,
wall.
so this is falling, but the rope is holding it this way. A bridge.
No, that's going down. Force is going down.
No, the
It's
strong,
compressing.
the force on the beam is pulling this way. Because there is here.
I don't know.
Here.
Anyways, context is important here too. Okay, that's tensile strength. Oh, I already looked at the graph. When we already looked at that. The relationship is that they're proportional. Alright, so here are some values of Young's modulus for different materials. So, for a material like rubber, you have 0.1 times 10 to the 9 pascals.
Minus 1 times 10 to the power of 8.
You'll see why soon. Yeah, why not? Good question. I'm sure I had a reason when I typed this.
Is that 1 power 9?
Possibly. You all know rubber? Yes. Is it a rubber? Yeah. It's not some synthetic.
It has to be rubber for it to jump.
Does it have to be
No,
rubber?
it
No.
jumps because it has air in it. But this is very grippy, just like
Ah, tire. Car tire. Anyways.
Same material.
Huh?
Same material.
Yeah? Okay. Nylon. Does anyone know nylon?
Yeah, fishing rods.
Good. The rope? Or the rod? The thread, yeah.
String.
No, I don't think it's called string. I think it's called line, actually.
Fishing line.
Fishing line, yeah. But that's better. I was calling it rope, and I realised that's stupid. It's not rope. You can't climb it. Fishing line, yeah. Okay, that's nylon. Wood. So can you see the difference between a material like rubber and wood? It's 100 times different. 100-fold difference. So that means wood is 100 times stiffer than rubber. Do you get what I'm saying? Yeah. Okay, so next material is glass, which is 7 times stiffer than wood.
What do you mean by that?
Yeah, like the Young's modulus is 7 times bigger, which means the K is 7 times bigger, which means it's like you need 7 times more force to have the same effect.
Of course, you need to bend it.
Yeah. Deform it. Yeah. Okay. Next is brass, which you can see is 1,000 times stiffer than rubber, 10 times stiffer than wood. Brass being, well, not that, but something like that. Usually door handles and things are made of brass.
Nahas.
Huh?
No, it's called nahas.
Brass? Okay, you got that? Next, copper, even stiffer. Continue. Next, we have steel, stiffer again, 2,000 times stiffer than rubber, twice as stiff as brass, 20 times stiff as wood. Right, so you've no book out.
I'll take a picture of the table. To help me solve the question.
Yes. Graphene, 10,000 times stiffer than rubber. And I think that's a mistake on my table because there's nothing after it. Okay, you have that? Yes? Yes? Okay, continuing. Let's do this question together. A boy hangs a 100-gram mass at the end of a 1.5 meter copper wire which is attached to the ceiling, and the wire is 2 millimeters thick. So I'll just draw that for you. You have a wire and its thickness is 2 millimeters, and I said it's 1.5 meters long, and then the boy hangs a 100-gram weight at the end. And the first question is, what is the cross-sectional area? That's this area here. So I want you to get that for me. It shouldn't be too difficult. The area of the circle here, it's 2 millimeters thick. I want the answer in meters squared, of course. So first question is, what is the area? You have it? Got it? Ugh. Okay. So what's the formula here you use? Area equals pi r squared. And what's the r? 0.001 squared, which is equal to 0.000001 pi, which is 0.00000. I can do this without a calculator. 1, 2, 3, 4, 5. Yeah, that's 10 to the minus 6, isn't it?
3 point, yeah.
I guess 3.1415 times 10 to the minus 6 meters squared. Okay. What?
Times 1, that's to be fine.
I know that. And you know that. What's wrong? No. Good. Okay. B. What is the stress? So stress is force over area.
Yeah. What's the weight of the thingy?
If only I said it in the question.
Yeah, but the thingy, the drawing was nice.
But it says it in the question.
Okay.
You like my drawing? Thanks.
Gigantic answer.
Gigantic because the area is small. Okay. Got an answer, people?
Yes.
Got the right answer? I hope so. Stress is force. Can you see that okay? There. Stress is force over area, and the force here is the weight, and the weight here is mg. So this is 0.1 times 9.81 over 3.1415 times 10 to the minus 6. So that's, what's that? 0.981 over 3.1415 times 10 to the 6. 312,000. So that's 312 kilopascals. Yes? Yes. Yeah. Okay, C. Probably guess if you don't remember what would be next if I just asked you for. You guys are smart. Okay, next is the strain, please.
Do we have everything?
Yes. table. 2.7 times 10 to the power -6.
Unbelievable. Yeah, okay. So, you have two formulas here. You have strain equals extension over length, which is no good here, because you don't know the extension. But you also have Young's modulus equals stress over strain. So this means strain is stress over Young's modulus. Did we work out the stress? We did. And what's Young's modulus for this material known as copper? What is it?
117 times 10 to the fourth.
So the final answer here, please?
2.7 -6. Yeah.
Okay. D. Is it the extension? What's the extension? Okay. Off you go. Got it? Right, so what formula here, Yusuf?
Strain times
Strain equals extension over length. So that means, yes, strains by length, which is 2.7 times 10 to the -6 times, what was the length?
1.5.
So what's 2.7 times 1.5? Now I can do this. 4.1 micrometers? What?
4.003.
Okay, 4 micrometers.
Yes.
As close. Right, E. What is the K? So what's the K?
What was the topic that we studied yesterday?
Sleepy time, how to sleep in class.
Oh, the thing is the topic.
Oh, sorry. Physics, materials, sleepy time. You remember? The hookish materials.
What's your name?
Oh, we said this yesterday.
I have something.
Newtons per meter.
Really?
Got an answer? What formula do you use here? Yeah. F is equal to K delta X or X or whatever. So that means K is equal to F over extension, which is weight over extension, which is mg over extension, which is 0.981 over 4 times 10 to the minus 6, which is a big number, I would think. 245 kilonewtons per meter. You could also use that formula too.
Where is your
A little longer though. Yeah. What? What's wrong?
I will ask the question.
He did it.
Omar?
Can I go?
Okay. Continue.
Yeah.
Next. 4 metal beams of 2 by 2 by 2 cm are used to support a platform. The platform of mass 3,000 kilograms is suspended from the beams like an upside down table. When 1,000 kilograms is placed on the platforms, the beams extend a total of 2 millimeters. So I'll draw that for you. Here is the platform. And then you have 4 of these beams. Ugh. You know what I'm doing. Close enough. Right, so what happens is you put a big weight on this of 1,000 kg, 1,000 kilograms. And when you do, this extends by 2 millimeters. So my first question is, what is the strength? You know what, let me write all the information in. This here is 2 meters, and this by this is 2 centimeters. 2 centimeters. And the mass here is 3,000 kilograms. And my first question is, what is the strain on each beam? So, what's the formula for strain? Extension over length. So, what is the extension here? 0.002. And the length, 2. So that's 0.001.
Is it 0.002?
What? What's wrong?
Is the extension 0.002 or 0.02?
That would be 2 centimeters. I don't know who this person is and I don't want to talk to them because I'm hungry. Okay. B. Is that okay? Right, B. What is the stress? Stress equals force over area. And what's the force? The weight. And what's the weight?
9,000 times 9.84. 1,000 G.
1,000 G. Yeah. 1,000 G. And the area?
0.02 cubed.
You're always mixing that up. Squared.
Oh, because the area. Okay.
Yes. Now, do I want the total? Now, I said I want on each.
That's why.
Yeah. So, if it's on each beam, I should only look at one of the beams, like this one here. So, in a way, I should divide this by 4, because this is being shared on the 4 of them. Yeah. So, once you get your answer, divide it by 4, and tell me what you get. Because you're just looking at 1 here. What do you get?
6131250.
Yeah? So, what's that? 6.13 megapascals? Yeah. Right, C. What is the Young's modulus? Well, that's stress over strain, isn't it? So that's 6.13 times 10 to the 9 pascals. Okay, D. By how much more will the beams extend if another 1,000 kilograms is placed on it? So we can use the formula strain is extension over length. So that means extension is strain by natural length. Yes? Although actually, do we know the strain? No, this won't do. We'll have to go with Young's modulus is stress over strain. So that means strain is stress over Young's modulus. Now we know the Young's modulus and we can get the stress, because what's the formula for stress? Force over area, which in this case is weight. And what's the weight now? 2,000 G. But if we're just looking at one beam, over 4. So we'll divide this answer by 4. And the area is 0.02 squared. And the Young's modulus, we just worked it out, it's 6.13 times 10 to the 9. So I'm thinking the answer here should be 4 millimeters. What is it?
0.002, which is like 2 millimeters.
2 millimeters. Half of that. Rats. Rats. You didn't make a mistake, did you?
No, I got this.
Can't trust both of us. We need a third person.
But that doesn't make any sense. Give me the calculator. It is 2 meters long, I said, didn't I? Is it still on the calculator? Ah.
I got. Yeah, the same ones. Andrew's got the same ones.
Oh, so then it must be right. Is that what you're saying?
Yeah, because these people got the same ones.
But my spider senses tell me something is wrong. Howdy.
Hey, listen a second.
No, finish in 30 seconds.
Alright, Grant.
Sorry, I'm not happy with people getting the right answer. The heck?
You don't always have to be right, Mr. Steve.
Yeah.
I was expecting 4 though. Can I trust you with these answers? This is this, isn't it?
This is this. Yeah, it's logic.
Oh well. I guess it's right. I guess I should believe in myself. Or no, I should believe in you. Alright, out we go. Oh yeah, if you need... after lunch is maths, correct? Yes, okay.